There is a metal sitting inside your body right now, and you have been putting it there every single day without knowing it, without choosing it, and without any way to stop it once it is already in. I want to be honest with you from the very first second. When I started digging into element number 48, I thought I was going to find a moderately interesting chemistry story, something for a curious afternoon. Instead, I ended up surrounded by stacks of research papers, old court transcripts, declassified wartime physics reports, and Nobel Prize documentation. And the deeper I went, the more one thing became clear. This is not a story about a chemical element. This is a story about how one invisible material managed to show up at almost every major turning point of modern science and modern civilization, and how almost nobody noticed it was there. We are talking about a metal that played a direct role in the first controlled nuclear reaction in human history. A metal whose atomic-level behavior unlocked a technology that earned a Nobel Prize in chemistry just recently, more than 40 years after the original discovery. A metal that right now, at this exact moment, is slowly accumulating in the kidneys of a large portion of the global population through nothing more exotic than a standard daily diet. It has been inside the control systems of nuclear reactors since the very beginning of the atomic age. It has been inside the pigments of some of the most famous paintings on the planet. It has been inside thin solar panels generating electricity in sunlit fields across multiple continents. It has been inside medical imaging detectors helping doctors identify tumors at earlier stages. And it has been inside the screens of televisions and monitors, hiding behind a brand name that made it sound futuristic and clean. None of those applications were planned from the start. Each one was discovered by accident, developed under pressure, deployed before the full picture was understood, and then handed to the next generation to deal with the consequences. I spent a long time with this element, not in a laboratory, not in a reactor room, but in the way that a person spends time with something when they cannot stop pulling on one thread because every pull reveals three more. I read the studies, I read the legal records, I traced the patents. I followed the careers of the scientists involved, some celebrated, some almost completely forgotten, separated by decades and by geopolitical walls that were never supposed to let information pass through. And when I finally had the full picture assembled in front of me, the thing that stayed with me was not any single dramatic moment, it was the pattern underneath all of them. The same shape repeated across completely different contexts. Knowledge arrives, the world takes its time. Something eventually forces a response. And by then, the cost has already been paid by people who never got to see the outcome. That pattern starts not in a laboratory or a reactor or a factory. It starts in a violent event so far from human experience that the scale of it is almost impossible to hold in your mind. And it starts, like most things that matter, long before anyone was looking. Friends, if this kind of deep scientific storytelling is what you want more of, please subscribe and leave a like. It genuinely helps this channel keep going, and there is a lot more of this story still to tell. So here is where element 48 actually comes from, and I want you to understand that this is not a metaphor or a dramatic opener. This is the literal physical origin of every single atom of this metal that has ever existed on Earth. Ordinary stars cannot make it. The Sun, which has been burning for nearly 5 billion years and has enough fuel to burn for roughly another 5 billion, reaches a hard limit when it tries to build heavier and heavier elements through nuclear fusion. That limit sits around iron. Past iron, fusion stops releasing energy and starts consuming it. So the Sun cannot go further, it never will. To produce element 48, you need something far more extreme. You need two dead stellar remnants, objects so dense that a teaspoon of their material would weigh more than all the vehicles ever manufactured by humanity combined, colliding with each other at a significant fraction of the speed of light. In the fraction of a second during that collision, neutrons pile onto existing atomic nuclei so rapidly that the normal rules of radioactive decay cannot keep up. Heavier and heavier nuclei are assembled in an instant. The debris is blasted outward across light-years of space. Some of it, billions of years later, ends up in a drifting cloud of gas and dust that slowly collapses under its own gravity and eventually forms a star with a small family of rocky planets orbiting it. Every atom of element 48 on Earth took that exact journey. A catastrophe in deep space, a cloud, a solar system, billions of years locked inside rock, and then eventually a surface where living things develop the ability to dig, smelt, and refine what the ground contained. But here is where the element does something that you have to appreciate for its sheer geological cleverness. It does not form large independent deposits. It does not announce itself in concentrated seams that a mining survey would circle on a map. Instead, it spends its entire geological existence hiding inside the crystal structure of a far more common and economically valuable metal. The atomic dimensions of its ion are close enough to those of its host that the crystal lattice accepts it without complaint. It fits. It belongs, geometrically speaking. And so it sits there, invisible, distributed, patient, waiting inside ore bodies that miners dig up for completely different reasons. The consequence of this is that every industrial operation that processes its host metal also produces element 48 as an unavoidable companion. The smelters, the refining systems, the electrolytic tanks, all of them capture it in dust, in slag, in liquid runoff. It is separated, purified, and sold. The global supply is not driven by demand for the element itself. It is driven by demand for the metal it hides inside. Which means the price stays low, the supply stays constant, and the element continues to flow into the world whether the world wants it at that moment or not. And the first person to pull it out of hiding and hold it up and say, "This is something new. This has never been formally identified," was not a scientist on a funded research mission. That detail matters, and we are going to get to it in the next part. Because the circumstances of that discovery tell you something important about how the most significant things are actually found. The man who discovered element 48 was not supposed to discover anything. That is the part that gets left out almost every time this story is told. His name was not attached to a university research program. He was not chasing a gap in the periodic table or following a theoretical prediction. He was a government inspector, the kind of person whose job exists to keep paperwork in order and catch violations before they become problems. His days were built around schedules, checklists, and the steady rhythm of moving from one location to the next. Show up, take a sample, run the standard tests, document the result, move on. On the particular morning that changed everything, he was processing a routine batch of industrial chemical samples at his workbench. One of them was a white powder, a zinc-based compound used in several commercial applications at the time. The standard test for this material was simple and well understood. You apply heat. The compound breaks down and leaves behind a white residue. Every trained chemist in that era knew the result before they ran the test. White in, white out. Predictable, unremarkable, done. The residue that came out of the crucible was not white. It was a dull, unmistakable yellow, the color of old bone or dried sulfur. He stood there in the warm, slightly chemical-smelling air of his workbench space and looked at it for a long moment. The color sat there in the dish and did not explain itself. Now here is the fork in the road. A person doing a compliance job, under no pressure to investigate anomalies beyond what the checklist requires, has a completely rational and professionally acceptable option available. Log the sample as contaminated. Write up a violation for substandard product quality. Move to the next address on the schedule. The day ends on time. Nothing changes. He took the sample back to his personal workspace instead. What followed was not a dramatic breakthrough in a gleaming laboratory. It was weeks of slow, methodical, unglamorous chemical work. Dissolving the material in acid, precipitating specific compounds out of solution, filtering, heating, purifying again, removing every component he could identify and account for until only the unidentified fraction remained. What sat at the bottom of the vessel at the end of that process was a small amount of a soft, silvery white metal with properties that matched nothing already documented. The density was wrong for zinc. The melting point was different. The way it responded to various chemical reagents was its own. It was not a contamination. It was not an error in the process. It was something that had simply never been formally separated and named before. He called it after the ancient term for the ore it hid inside, which translates roughly as the metal within the metal. A name that is less a label and more an accurate description of a geological fact. And this is where that detail from the previous part connects directly. The reason it had never been found before was not that it was rare in any absolute sense. It was that it never announces itself. It sits inside the crystal structure of its host, geometrically indistinguishable to any process that does not specifically go looking for it. It took a person who refused to accept a wrong answer and walk away to finally pull it into the light. The story could end there and already be interesting. A bureaucrat with curiosity makes a discovery that changes materials science. But Element 48 was just getting started, and the next chapter of its story involves something that seems completely unrelated at first. Canvas, oil paint, and the obsession of a generation of artists with a color that nobody had been able to make properly before. The painting hanging in the conservation lab did not look damaged. That was exactly the problem. A materials scientist named Dr. Elena Marsh had been brought in to assess a collection of late 19th century works held at a major European institution. Her specialty was non-destructive analysis, meaning she could examine the molecular composition of a painting's surface layers without taking a single sample, without touching the canvas, without leaving any mark. The technique used a focused beam of X-ray energy directed across the surface. The atoms in the paint responded by emitting their own characteristic signals, like a fingerprint read from a distance. What her equipment showed her inside one of the most visually striking works in the collection was not what anyone in the room wanted to hear. The rich, saturated orange-yellow pigment that dominated the lower half of the canvas, the color that gave the painting much of its emotional force, was undergoing a slow chemical transformation inside its structure. Not on the surface where the eye could catch it. Deeper, at the layer where the pigment particles bonded to the oil medium. The compounds were oxidizing, slowly, continuously. And in the perfectly climate-controlled air of one of the most carefully managed storage environments that money and expertise could create. To understand why this mattered so much, you have to go back to what that pigment actually was and why artists had reached for it so eagerly in the first place. Before Element 48's sulfide compound became commercially available as a pigment, painters working with warm yellows, oranges, and reds were fighting a losing battle with their own materials. The available options each carried a serious flaw. Some faded in light faster than the artist could finish the series. Some produced tones that looked muddy and flat compared to what the painter saw in the natural world. Some reacted badly with other pigments on the palette and shifted color over time in ways that could not be predicted or controlled. The cadmium-based pigments solved almost all of those problems at once. The color was intense and clean. It held its saturation under prolonged light exposure far better than the alternatives. It survived the heat of industrial applications that would destroy organic colorants. Artists who worked with it described the experience of finally having a warm tone that behaved like it was supposed to behave. An entire generation of painters built some of their most recognized works around this pigment. The warm fields, the glowing interiors, the heavy summer light in canvas after canvas from that period all carry its signature. And now, Dr. Marsh was standing in a conservation lab, explaining to the collection's curators that the same pigment that had made those colors possible was under certain atmospheric conditions, even inside controlled museum environments, capable of converting into colorless degradation compounds. The color was not going to vanish overnight. The process was slow enough that annual visual inspection would show nothing, but it was not stopping. What her team did next was as important as the finding itself. Rather than treating the discovery as purely a damage report, they developed a systematic monitoring protocol using the same non-destructive scanning method. Baseline measurements for every at-risk work in the collection. Repeat scans on a regular schedule. A database of molecular-level change tracked over time, so that any acceleration in the degradation process could be caught and addressed before it became visible and therefore irreversible. The element that had come out of a bureaucrat's crucible as an oddity, that had become one of the most prized materials in the history of painting, was now requiring an entirely new branch of conservation science to protect the legacy it had helped create. And the deeper you look at this pattern, the more you realize it is not a coincidence. It is a signature. Because the same quality that makes element 48 extraordinarily useful in application after application, its ability to sit quietly inside other systems and do something remarkable without drawing attention, is also what makes the consequences of its presence so easy to miss until they are already well underway. We are going to see that pattern again very shortly, in a context that is significantly more serious than a painting. If you had walked into that basement space on the night the first controlled nuclear chain reaction was initiated, the thing that would have struck you first was not the science. It was how ordinary the whole setup looked, and how terrifying that ordinariness was. No gleaming facility, no reinforced walls, no automated systems with blinking indicators. Just a large, cold, dimly lit space beneath the concrete stands of a public stadium, filled with the smell of graphite dust that coated every surface and settled into the lungs of everyone who spent time there. Stacked blocks of material, hand-placed over weeks by a rotating team of workers, forming a rough gray structure that looked more like a construction project than the most consequential physics experiment in human history. The team that built it knew exactly what they were attempting. They also knew that if the reaction accelerated beyond the point where it could be brought back under control, there was no containment structure around them. The city above them had no idea any of this was happening. The experiment was classified at the highest level because there was a war on, and the military implications of a controlled nuclear reaction were not abstract. They were the entire reason the project existed. Control of the reaction came down to a set of rods that could be inserted into the core to slow it down, or withdrawn to let it accelerate. And the material those rods were made from was element 48. Specifically, a coating of it applied to the rod surfaces. The reason comes down to a single nuclear property that this element possesses to a degree that almost nothing else in the periodic table can match. When a neutron traveling through the reactor core approaches a nucleus of one particular isotope of element 48, the probability that the nucleus will simply absorb that neutron and stop it from causing further reactions is extraordinarily high. The technical measurement for this probability is expressed in units called barns, a term physicists coined with a certain dry humor because the target seemed, on nuclear scales, almost impossibly large to miss. Most elements have neutron capture values measured in single digits or low tens. This isotope of element 48 measures around 20,000. It does not slow neutrons down, it consumes them. Insert the rods deeper into the core and more neutrons are absorbed before they can split uranium nuclei and release the next generation of neutrons in the chain. The reaction slows. Pull the rods back out and the neutron population grows. The reaction accelerates. The physics team on that night had a person stationed at the control position whose entire job was to monitor the instruments and adjust the rod position in response to what the readings showed. The reaction ran. It was controlled. It was stopped. A coded message was sent to confirm success, deliberately vague enough that it would mean nothing to anyone who intercepted it on an open line. The team went home through the cold night air with graphite dust still on their hands and their clothes. That same control principle, element 48, absorbing neutrons to regulate the speed of a fission chain reaction, has not been replaced or fundamentally improved since that night. The materials are refined, the engineering is vastly more sophisticated. The safety systems have multiplied into layers of redundancy. But in nuclear facilities operating right now on every continent where civilian or research reactors run, the core logic of how you turn the reaction up or down traces directly back to the properties of this element that a government inspector pulled out of a contaminated powder sample in a modest workroom. The inspector found it. The physicist weaponized its properties in the service of control. And the world has been living with both of those facts ever since. But here is what I keep coming back to when I think about this particular chapter of the story. The element that held the first nuclear reaction in check was never chosen for that role through grand design. It was chosen because its physics happened to be exactly what the situation required. The same way it hid inside zinc ore for geological ages because its geometry happened to fit. The same way it ended up in artist paint because its light stability happened to solve a problem nobody else could crack. This element keeps arriving at critical moments not because anyone planned it that way, but because its properties keep matching the needs of the moment. That pattern will matter a great deal when we get to what happened next in a farming valley on the other side of the world. A community of farming families living along a river valley had been eating food grown in the same soil for generations. The river ran down from the mountains, carrying water that was clean enough in appearance, cold enough in winter that you could see your breath above it on still mornings, and familiar enough that nobody questioned it. You irrigated with it because your parents had, and their parents before them, and the rice grew well, and that was the shape of life in that place. Upstream, beyond the ridgeline where the mountains began, there was a large industrial operation extracting zinc ore from the rock. The processing of that ore produced wastewater. The wastewater went into the river. This was not considered a problem at the time because there was no regulatory framework that classified it as one. No measurement requirement existed. No permitted concentration limit had been established for heavy metals in agricultural water. The concept itself was absent from the legal and administrative landscape. The water looked fine. The rice grew. Life continued. Element 48. That geochemical companion of zinc that always appears wherever zinc is processed, entered the river in the wastewater. It settled into the soil of the irrigated fields. The rice plants drew it up through their roots along with the water and minerals they needed to grow, and concentrated it in the grain. Families ate rice every day, as they always had, because it was the primary food source in the region, and there was no particular reason to change that. The accumulation in their bodies was completely silent for years. This is one of the most important and most unsettling facts about element 48 as a biological hazard. It does not announce itself. There is no immediate signal, no taste, no smell, no acute reaction that would connect cause and effect for a person experiencing it. It simply builds, year after year, stored primarily in the tissue of the kidneys, held there by the body's own protective mechanisms, working exactly as they were designed to work. A local physician named Dr. Haruto Seki began keeping systematic records after he noticed that the pattern of bone-related illness in the valley did not match anything in the standard medical literature he had access to. The patients he was seeing presented with pain severe enough that movement became something to dread. Fractures occurred under loads that healthy bone structure would absorb without consequence. The skeletal damage progressed in ways that conventional nutritional deficiency explanations could not fully account for. He mapped the cases by location. The geographic concentration was not random. It followed the irrigation network downstream from the industrial site with a clarity that was difficult to dismiss once you saw it drawn out. He published his observations and proposed that industrial contamination of the water supply was the mechanism behind what he was seeing. The company's response was immediate and organized. A team of consultants produced alternative explanations. Each one was individually plausible. Wartime and post-war nutritional stress. Physically demanding agricultural labor over many decades. Local environmental factors unrelated to the industrial operation. The scientific debate that followed was not a genuine exchange between equally positioned parties. On one side was a regional doctor with case records and a map. On the other was a well-resourced company with a strong financial interest in the outcome and the institutional connections to make proceedings move slowly. And what happened next in the courtrooms and regulatory offices of that country is one of the clearest examples on record of exactly how long the gap between documented knowledge and official action can be stretched when the right pressures are applied. Element 48 does not poison you the way most people imagine poisoning works. There is no single moment, no dramatic event, no clear before and after. What it does is far more patient and far more precise than that, and understanding the mechanism at the cellular level changes how you think about the entire story of this element. The key is in how it moves through the body in the first place. The ion form of element 48, meaning the atom after it loses 2 electrons and becomes chemically active, has dimensions that are close enough to 2 essential biological ions that the transport proteins embedded in cell membranes do not reliably distinguish between them. Those transport proteins evolved over millions of years to recognize zinc and calcium by their physical geometry and move them across the membrane barrier into the cell. Element 48 fits the recognition pattern well enough to get waved through. Not always, not perfectly, but with enough frequency that in a body receiving regular low-level exposure, it accumulates steadily over time in tissues that depend on those transport systems. Once inside the cell, it does not behave like the ions it impersonated. It binds to enzymes that were built around zinc or calcium and disrupts their function by replacing the working part with something that cannot do the job. The cell's biochemistry begins to run incorrectly in ways that are too small to register as symptoms at first, and too numerous to trace back to a single cause by the time they accumulate into something noticeable. In the kidneys, the situation has a specific additional layer that makes it particularly serious. The kidney tissue produces a small protective protein whose job is to bind incoming heavy metals and hold them safely away from other cellular machinery. This protein does its job correctly. It finds the element 48 ions and locks them down. The problem is that the kidneys then become the storage site for everything the protein has captured. The element does not get cleared. It accumulates in exactly the organ responsible for filtering the blood and maintaining the body's mineral balance. The half-life of element 48 in human kidney tissue is somewhere between 10 and 30 years. Read that again if you need to. Not days, not weeks, years, decades. If you are receiving regular dietary exposure to this element starting in early adulthood, which the evidence strongly suggests most people in industrialized countries are, then you are building a deposit in your kidney tissue across your entire adult life. And when the concentration in those cells crosses a threshold that research places at roughly 100 to 200 micrograms per gram of tissue, the filtering function begins to fail in a specific way. Calcium and phosphorus that should be recaptured from the primary filtrate and returned to the blood are instead allowed to pass through and leave the body in urine. The bones, which depend on that recaptured calcium and phosphorus to maintain their structure, begin to lose their mineral density gradually and silently. This is the biological mechanism that Dr. Seki was observing in the farming valley without yet having the tools to fully explain it. The patients he was documenting were not showing acute toxic reactions. They were showing the end point of a process that had been running inside their bodies for 20 or 30 years before the first symptom appeared. By the time bone fractures were occurring from ordinary daily movement, the accumulation was already decades old and entirely irreversible. The International Cancer Research Authority has since placed element 48 in its highest certainty category as a substance that causes cancer in humans. The clearest evidence connects inhalation exposure to lung cancer. Established through long-term studies of workers in industrial settings, evidence for kidney and other tissue involvement continues to strengthen as the research base grows. The mechanism proposed is that the element interferes with the cellular systems that identify and repair damage to DNA. Every cell in the body experiences DNA damage continuously as a normal result of biological processes. Usually, the repair machinery catches it and corrects it before it matters. Element 48 can disable parts of that repair system, leaving errors in place to accumulate across cell divisions. This is the slow version of harm, the version that takes decades to manifest. The version that is almost impossible to connect to its source without systematic epidemiological work across large populations. And the detail that closes this chapter of the story is the one that should stay with you. There is no established medical intervention that effectively removes this element from kidney tissue once it is there. The treatments that work for some other heavy metal accumulations cannot be applied here without risk of mobilizing the stored element and causing additional damage during its movement through the body. You manage the consequences, you cannot undo the accumulation. That is the biological reality. Which brings us directly to the question of where the exposure is actually coming from for the vast majority of people who have never worked in a mine or a factory. And the answer is somewhere that almost nobody expects. Two researchers who had never met, who could not correspond, who worked inside systems that were officially opposed to each other on every level that mattered, made the same discovery within 2 years of each other. That fact alone would be interesting. What happened afterward is what makes it one of the most compelling episodes in the modern history of science. The first was a physicist named Dr. Vasily Orlov, working at a state optics institute in a Soviet city in the early 1980s. His institute worked with specialized glass for optical and military applications, well-funded, tightly controlled, and not particularly interested in publishing results for an international audience. The glass he was analyzing contained nanocrystals of a cadmium-based compound embedded in the melt. Colored glass made with cadmium compounds was ancient technology. Cathedral windows across medieval Europe owed their warm amber and orange tones to cadmium pigments dissolved into molten glass. Nothing about the basic material was new. What Orlov noticed was specific and strange. Samples with identical chemical compositions were producing different colors. Same formula, same base material, different results. The color of a substance is determined by its chemistry and its crystal structure. This is one of the foundational principles of materials science. The physical size of the sample does not enter into it. A large piece of gold and a fine powder of gold are both the same color. Everyone in the field understood this as a given. Orlov started measuring the crystal sizes in his different samples using X-ray scattering techniques and found a pattern that should not have existed. Samples where the embedded crystals were larger produced one color. Samples where the crystals were smaller produced another. The color was tracking with size, not with chemistry. He ran the measurements again. The pattern held. He wrote up the results and published them in a Soviet physics journal. The paper was translated into English as part of a standard exchange program. But it landed in a literature that Western researchers in this particular field were not systematically monitoring. Almost no one outside the Soviet scientific community engaged with it. 2 years later, a chemist named Dr. Martin Reeves at a private research laboratory on the American East Coast was working with cadmium sulfide nanocrystals suspended in liquid solution rather than embedded in glass. He synthesized batches with different particle sizes and found exactly what Orlov had found. The optical properties of the crystals depended on their size. He published in a major international chemistry journal, and the scientific community responded immediately. The work circulated widely. Follow-up experiments were designed and run within months. The explanation for both observations lies in what happens to electrons when you confine them inside a structure that is smaller than about 10 nanometers. In a bulk crystal, electrons can occupy a continuous range of energy states. In a nanocrystal, the confinement forces the allowed energy levels to become discrete, like steps rather than a slope, and the spacing between those steps depends on the size of the crystal. When an electron absorbs energy and then releases it as light, the color of that light is determined by the size of the step it falls across. Smaller crystal, wider spacing, higher energy, bluer light. Larger crystal, narrower spacing, lower energy, redder light. By controlling the size of the crystal during synthesis, you can produce any color across the visible spectrum from a single chemical compound. This is dimensional quantization, and it is the foundation of an entire field. The technology that eventually grew from this discovery appears in medical imaging systems that track individual labeled cells inside living tissue in real time. It appears in cancer research, where specific cell types can be marked and followed through biological processes that were previously invisible to observation. And it appears in the screens of televisions and monitors manufactured under various brand names that made no mention of the chemistry underneath. In those consumer devices, nanocrystals of cadmium compounds were producing colors of a purity and precision that previous display technologies could not achieve. Orlov's priority was eventually established through careful reconstruction of the publication record. Reeves acknowledged it directly and publicly when the history became clear. The Nobel Committee, when it finally awarded the prize for this discovery and the subsequent development of the technology, divided the recognition equally between the researchers who had each found the same truth from opposite sides of a wall that was never supposed to let anything through. Orlov was in his late 70s when the award was announced. More than 4 decades had passed since the morning he looked at 2 chemically identical glass samples producing 2 different colors and decided that the explanation could not be what everyone assumed it was. The food you ate today almost certainly contained element 48, and nobody on the packaging was required to tell you that. I want to be precise about this because it is easy to hear it as a dramatic overstatement and dismiss it. It is not an overstatement. The pathway is documented, measured, and published in the assessments of major food safety authorities across multiple continents. It does not involve industrial accidents or contaminated water supplies or any of the dramatic scenarios that come to mind when people think about toxic metal exposure. It involves fertilizer and wheat and potatoes and the quiet arithmetic of accumulation across decades of normal eating. Here is how the chain works. Phosphate rock is the raw material used to manufacture the phosphorus fertilizers that modern agriculture depends on. Phosphate rock is a sedimentary material, meaning it formed over geological time from the accumulation and compression of organic material on ancient seafloors. During that formation process, element 48 was incorporated into the mineral structure alongside the phosphorus, because geochemically they tend to occur together in sedimentary environments. The concentration varies by deposit location, but in some of the most heavily traded phosphate sources, the cadmium content runs to several tens of milligrams per kilogram of rock. Standard fertilizer manufacturing transfers a significant portion of that cadmium into the finished product. The fertilizer goes on to agricultural fields, It has been going on to agricultural fields across Europe, North America, and large parts of Asia for the better part of a century. Cadmium does not wash easily through the soil profile into deeper layers. It binds strongly to organic matter and clay particles in the topsoil and stays there. Each application adds a small increment. Decade after decade, the concentration in the arable layer builds slowly upward. Cereal crops, root vegetables, and oil-bearing plants draw water and dissolved minerals up through their roots without a filtering mechanism that distinguishes between cadmium and the nutrients they need. Wheat concentrates what it absorbs primarily in the grain. Potatoes accumulate it in the tuber. Sunflowers pull it into the seeds. The food that comes off those fields carries the element 48 that the soil has been collecting since before most of the people eating it were born. A major food safety assessment published by a European regulatory authority examined dietary cadmium intake across the general population and reached a conclusion that caused considerable discomfort in the agricultural industry. A substantial portion of ordinary adults in countries with traditional grain and vegetable-heavy diets were already at or above the tolerable weekly intake level for cadmium. Not people with unusual occupational exposure. Not people living adjacent to industrial sites. People eating bread and potatoes and leafy greens in the quantities that a standard healthy diet recommends. The regulatory response was real, and it was not nothing. Maximum permitted levels of cadmium in several food categories were lowered. Standards for cadmium content in phosphorus fertilizers were tightened, with further reductions scheduled on a defined timeline. Monitoring programs were expanded. These are genuine actions that will, over time, reduce the rate at which cadmium enters the food chain. But here is the part that the regulatory announcements do not emphasize. The cadmium that is already in the topsoil of agricultural land across wide regions of the industrialized world is not going to be removed by changing the fertilizer standard. It is bound there. It will continue to be taken up by crops grown in that soil for generations. The new rules slow the rate of future addition. They do not address the existing accumulation. The fields are already carrying decades of deposits, and the crops growing in them right now are drawing from that reservoir, regardless of what the current fertilizer label says. For people who smoke, the numbers are notably worse. The tobacco plant has an unusually high capacity to absorb cadmium from soil, and when tobacco burns, the element passes into the smoke and is absorbed through the lungs with dramatically higher efficiency than through the digestive system. Long-term smokers carry a body burden of cadmium that research consistently measures at 2 to 3 times the level found in non-smokers with identical diets. The lungs deliver it directly into the bloodstream at a rate that the gut, with its more selective absorption processes, simply cannot match. The accumulation in the body that we described in Part 7, the decade-long buildup in kidney tissue with no reliable mechanism for removal, is being fed by these two channels simultaneously for a large portion of the global population. Every day, silently, in food that looks clean, tastes normal, and carries no warning of any kind. Every single application of element 48 that we have covered in this story followed the same invisible arc, and I want you to see it clearly before we finish, because it is not a coincidence and it is not ancient history. The farmers in the valley downstream from the zinc operation did not know what was accumulating in their rice for the first 2 decades it was happening. The artists who worked with cadmium pigments did not know their most beloved colors carried the architecture of their own slow destruction. The consumers who purchased rechargeable electronics in the first wave of portable technology had no idea that the batteries inside them would eventually leach into groundwater around landfill sites across the developed world. The agricultural systems that applied phosphate fertilizers to fields for generations were not hiding information. The information simply did not exist in a form that demanded a response. But then, at a certain point in each of these stories, the information did exist. Studies were published. Mechanisms were described. Geographic patterns were documented. The evidence moved from suggestive to solid. And in every single case, the time between that point and the point where binding regulation appeared was measured not in months, but in years, and sometimes in decades. During that interval, the exposure continued. This is not a story about ignorance. Ignorance is the period before the studies exist. What fills the space after the studies exist is something different. It is the friction of changing systems that are generating profit in their current form. It is the time required to move findings from specialized journals into the awareness of regulatory bodies. It is the delay introduced by industry consultation processes, by legal challenges to proposed standards, by the political difficulty of telling an agricultural sector that the fertilizer practices of the last century have left a problem in the soil that the next century will have to manage. Element 48 is still being produced right now, inevitably and continuously, as a byproduct of zinc processing. It is still going into nuclear reactor control systems. It is still present in the cadmium telluride solar panels generating clean electricity in fields across multiple continents, where the question of end-of-life recycling at industrial scale has not yet been fully answered by the regulatory frameworks currently in place. It is still being used in the most precise medical imaging detectors available for identifying abnormal tissue at the earliest detectable stage. It is still present in research laboratories, where quantum dot technology continues to be refined for biological and optical applications that did not exist a generation ago. The element is not a villain. It came from a stellar catastrophe billions of years before the Earth existed. It hid inside zinc ore for geological ages. A curious government inspector pulled it out of a contaminated powder sample through sheer refusal to accept an unexplained result and move on. Everything that followed, the paintings, the reactor, the river valley, the Nobel Prize, the fertilizer chain, the medical detectors, the quantum dots, all of it grew from that one moment of not looking away. The pattern of this element's relationship with humanity is not really about chemistry. It is about the distance between the moment we understand something and the moment we act on that understanding. That distance has a cost, and the cost is always paid by people who had no say in setting the timeline. The inspector who found element 48 was not supposed to make a discovery. His job was to process samples and issue violation notices and move to the next address. He did not have a theoretical framework that predicted a new element was hiding in zinc compounds. He had a yellow residue that did not match the expected result, and he chose to take it back to his workbench and find out what it actually was, rather than filing it as contamination and forgetting it. That choice, made in a quiet room with no audience and no reward attached to it, is why this story exists at all. Here is the question I want to leave with you. We now have more scientific information about the substances in our food, our water, our manufactured products, and our environment than any previous generation in human history. The tools to measure, monitor, and model the consequences of what we put into the world have never been more precise or more widely available. Given all of that, why does the gap between knowing and acting still exist? And who do you think is actually responsible for closing it? If this story made you think differently about something ordinary in your daily life, leave a comment below. I read every single one. And if you want more stories like this one, please subscribe and leave a like. It takes 2 seconds, and it genuinely changes what this channel can do.